Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on January 8th, 2026, about 6 days ago. It introduces a collaborative inference method that boosts accuracy by roughly 11% while cutting latency by 26% on the A25 benchmark, simply by routing tasks based on the very first token of a reasoning step. The paper is titled GlimpRouter, Efficient Collaborative Inference by Glimpsing One Token of Thoughts. And as we'll see later, the results suggest that a single initial glimpse is often enough to predict how hard a reasoning step will be. And for those interested in the implementation, the authors have shared their code on GitHub. To understand the core insight, Figure 1 compares the distributions of 4 different uncertainty metrics. The first two charts, displaying stepwise perplexity and entropy, show single central peaks, which implies that averaging uncertainty over a full sentence washes out the signal. The third chart, the judge score, is saturated at the high end, failing to capture nuance. However, the graph on the far right for initial token entropy tells a different story. It reveals a bimodal distribution with 2 clear clusters, a spike near zero for routine steps, and a wider curve for complex thoughts, which is ideal for deciding when to route. So Figure 2 takes that insight further by verifying if this entropy metric actually predicts whether the models agree. The authors plot the alignment between the small and large models' outputs against the initial token entropy. On the left, looking at the BLEU score, we see a sharp drop. When entropy is low, the models generate nearly identical text, but as entropy rises, their outputs diverge significantly. The chart on the right confirms this pattern using SBERT for semantic similarity, which suggests that high entropy correctly flags steps where the small model struggles to match the large model. Alright, Figure 3 maps out the GlimpRouter pipeline. It operates step by step. At the start of each unit, the small language model generates a single token, or glimpse, in the bottom track. The central layer then checks its entropy. For low uncertainty moments like step 1 and step 3, the small model finishes the step. But if the glimpse signals high complexity, like in step 2, it routes the context up to the large language model. Finally, on the right, the large model uses the full chain to produce the answer. So, Table 1 validates this pipeline across 5 benchmarks. The top row provides our efficiency floor with the SLM-only baseline. Moving to the bottom section, which uses DeepSeek 32B as the expert, notice the LLM-only row. GlimpRouter, in the final row, achieves a remarkable win here. On AMI25, it surpasses the standalone large model's accuracy, hitting nearly 52%, while reducing average latency by over 25%. Well, Figure 4 expands on this by plotting the sensitivity analysis across 4 benchmarks. Here, accuracy is on the vertical axis, and latency is on the horizontal one. The red connected circles represent GlimpRouter, while the blue triangles track the SpecReason baseline. Notice how the red curve consistently stays above and to the left of the blue one. This gap illustrates a superior Pareto frontier, meaning GlimpRouter achieves higher accuracy for the same amount of time spent. So, Table 3 investigates whether GlimpRouter works alongside other speedup tricks, specifically speculative decoding. This technique acts like a smart autocomplete, letting a small model draft tokens that the large model verifies. In the top rows, applying this to the standalone large model drops latency from 220 to 149 seconds on AMI25. However, the bottom rows reveal the winning configuration. Combining GlimpRouter with speculative decoding slashes latency to 130 seconds while maintaining that high of 52% accuracy. This proves the methods are complementary, offering compound gains in efficiency. Wrapping up, 2 takeaways stand out. The entropy of just the first token is a powerful predictor of difficulty, enabling GlimpRouter to improve both speed and accuracy without retraining. This suggests a future where models efficiently allocate compute by simply glancing at the problem first. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.